kind of have my hand to. Two of the lab sections, I'm going to introduce a chemical synthesis project. I'm going to take out one of the experiments that you're supposed to do, and I'm going to replace it with one reaction that we do inside my research for a grant and stuff. So if you happen to be in that lab section, I'll be doing 2 this semester. It'll be really fun. The reactions in water, guaranteed yield, not guaranteed high yield. But what I'm also going to teach for those 2 lab sections is microwave reactions. So the idea is I'm going to teach you about a reaction that we run in my lab for a molecule that we're going to need and we're going to use. And then at the same time as you start your reaction, running it for 2 hours, I'm going to take one of the groups in that lab section over to my lab and show them, I'll show everybody at one point throughout the day, the microwave reactor. I'm going to run that microwave reactor for the same amount of time and show you what the difference in yields are for the same chemical synthesis. Now you're going to get product in the teaching class, but you won't get product, you won't get as much product as the microwave reactor. So just let you know that I'm going to be taking 2 lab groups to do that. I don't have enough material to do all of them. And then anybody who's happens to be in those lab sections, I'll talk to you a little bit further about coming to what we call group therapy, which is my research group meetings on Fridays if you're available, just so you can learn a little bit more about what we do. That's not necessarily an invitation to join my research lab, but it's an invitation for you to sort of see the kind of stuff that we do and learn a little bit more about the field. So I thought I'd let you in on that. All right, aside from that, welcome back. We're in the chapter of aromatic systems. And what we've covered so far was the fact that we learned about conjugated systems. We learned that conjugated systems can be linear hydrocarbons where we've got that double bond, single bond, double bond character. Now we're talking about aromatic systems, which are also going to be conjugated, but within the ring system. And then, I mentioned that these aromatic systems have some inherent stability to them, just like the conjugated systems that we saw before, except what we find is that for aromatic conjugated systems, all those reactions, the substitution reactions, the dihalogenation, the bromination, all those oxidations from the chapter on alkenes, alkynes, none of that works in the aromatic ring. None of it, all right? And so then the question was like, well, how do we determine whenever you're looking at a system, whether or not it's aromatic or not? And so we sort of talked about what's known as Huckel's rule. And so again, this equation was one that you can memorize. So there's 2 ways that you can learn this. Either you memorize that equation and just know that what you need to do is replace the n with 0, 1, 2, 3, and 4. And if you do that mathematics, you're going to get the spit out, the output of 2, 6, 10, 14, 18. Right? And so that's one way you can memorize it. The other way to do it is just memorize the output. Just memorize this series. Okay? Now it's highly unlikely that you're going to see something with 18 pi electrons and try to determine the conjugate. It's highly unlikely. It's usually going to be somewhere, around here. And so the example I gave you was that the output for the Huckel's equation 4n plus 2 gives us how many pi electrons need to be conjugated in order to be qualified as an aromatic system. And so we started out with benzene. I said benzene has 3 pi bonds. Every pi bond is sharing 2 pi electrons. So in terms of the total number of pi electrons, it's 2, 4, 6. We go back to the Huckel rule output, and there it is, 6. And lo and behold, benzene is an aromatic system. All right. Another example we can look at would be cyclobutadiene. All right, so something like this. Right? Now, cyclobutadiene is a really good example because it does have the double bond, single bond, double bond motif. It is conjugated all around. But how many pi electrons does it have? 4, right? 2, 4. So this system has 2 double bonds, and thus 4 pi electrons. Now, if we look at the output, 2, 6, 10, 4 is not part of that output. And so something like cyclobutadiene, for example, is not aromatic. It's what we call anti-aromatic. It is extremely unstable. And so one of the things we learn about this molecule is it's highly reactive. It's highly reactive and it's unstable. And so isolating cyclobutadiene is not something that, we can usually do. And then the question might be, well, if it's unstable, what does it do? What is it doing? Well, the minute you generate it, it actually reacts with itself via a Diels-Alder reaction. So, we learned Diels-Alder in the previous chapter. And basically, one of these molecules is going to act as the diene. One of these molecules is going to act as the dienophile. And so when these two molecules, come together, the reaction is so quick that you can run it at negative 78 degrees Celsius, you get your Diels-Alder transformation. And what you make sort of transiently before it rearranges itself is this Diels-Alder product. So it is a bicyclic system. But then even this is unstable, so then what happens is this bond moves here, the electrons of that bond moves upstairs, and so the product of cyclobutadiene reacting with itself is the following cyclic structure. It looks like that. And so that is cyclooctatetraene. How many pi electrons does this have? Come on, spit it out. Hey, yeah, it's not early in the morning, so it's already noon. You just ate lunch and you're tired. Have a coffee. Yeah, it has 8, right? 2, 4, 6, 8. So is this aromatic? No. So cyclobutadiene is not aromatic, it reacts with itself, it produces a Diels-Alder product that undergoes cyclization further to produce a product that is 8 carbons in the ring, 4 pi bonds, and that product itself is also not aromatic. So what it means is we kind of focus on that final product. We can annotate our notes for that analysis. It's got 4 double bonds. And thus it has 8 pi electrons. And it is not aromatic. And because something like this is not aromatic, then we can say that it reacts like a polyene. Right? And when we say it reacts like a polyene, what we're saying is that all those reactions we learned in the chapter about kenes, this molecule can use and can undergo those transformations. And so polyene basically means we treat this molecule as if it has 4 different alkene bonds. They don't have that added stabilization that you see for aromatic systems. Right? So, having said that, if I were to control the reaction and say, let's say I expose it to 1 molar equivalent of Br2, then you need to remember what that does, right? Because this is just like I warned, chemical reactions coming from OChem1. Now, in this case, I'm going to draw the 1,2 dibromide upstairs, but any one of those double bonds could have done it. So you draw it on the double bond on the right, or on the bottom, well, it doesn't matter. But again, depending on who you took OChem1 with, you might not know what it means to have one equivalent. If I would have said excess bromine, then we would have generated 1,2 dibromo groups all around the ring, in which case you would have had 2, 4, 6, 8. If we would have statistically controlled it at 2 molar equivalents of bromine, then we would have done 2 of the double bonds and left 2 intact. Right? So in this case, I'm specifying 1 equivalent, and that definitely will react. Right? And so the point of this particular page of notes is so I can make the following statement, right? Is that fully conjugated rings pi electrons is not the sole requirement for aromaticity. And so it's not as simple as looking at cyclooctatetraene and saying, oh, it's got double bonds all around that are conjugated in the ring, that must be aromatic. It's not that simple. You have to look at the output for the Huckel's equation to match the total number of pi bonds to be able to make that conclusion. All right? And again, that's a really important thing, because if, for example, I was going to examine you over this concept, I might show you a molecule that may or may not be aromatic, and I may or may not be in a reaction scheme. And one of those options as an answer might be no reaction. One of those options might be the actual product of the reaction. And so surely if it was aromatic, then there would be no reaction. But if it wasn't, then you'd have to pick the product. Right? So, it's a little bit deeper than just saying, oh, I know that reaction, boom. It's like, no, because if it was aromatic, there'd be no reaction. And the answer to that would also be there, because I'm gonna be thinking, if I'm a student and I don't know this stuff, what might I think is the answer? And guess what? Dr. Wilson put that right there. So again, as usual, don't let the answer you come up with, because it shows itself on the exam, mean that you got it right. So you have to know this stuff well enough to know the difference. The other thing I was talking to students about, when you start getting to this stage of OChem, and you start to know this stuff so well, you might surprise yourself at how quick you come to the answer. And sometimes if you know the answer right away, you might be like, this can't be right. Then you start overthinking it, then you make the correction, then you come to my office and find out that you were originally right, and you can see where you erase the answer. Like, don't do that. It breaks my heart. It means you didn't trust yourself. Any questions about this? All right, so up until now, I've shown you examples of aromatic compounds that were neutral, right? When we first introduced, for example, the concept of resonance, we talked about resonating charges, whether they be cations or anions, and then I showed you the example of benzene and said, okay, well, here's resonance within benzene, it's a neutral compound. So you don't necessarily need charge in an aromatic system to have resonance. Well, the same is also true for aromaticity. You don't necessarily need to have a neutral molecule to be aromatic, all right? And so this next little bit is to try to show you that there are such things as aromatic ions, and what I'm going to try to teach you is how to determine when the aromatic ion that you're looking at, whether or not it's actually aromatic or not, right? So in other words, when you're looking at the Huckel output of total pi electrons, how do we come to the conclusion whether or not the ion we're interested in follows those rules or not? Okay, and so I'm going to draw cyclopentadiene. I'm going to draw it a little bit funky because I'm going to show you that the chemistry I'm going to do on this is going to be two possibilities. These hydrogens upstairs, so these are a CH2 upstairs. But I'm drawing the hydrogens there, going to show you that we're going to run some chemistry at that carbon and pull off those protons. Now, we can either pull off the proton, in which we take the hydrogen and the electrons that are holding it there, or we can simply take the atom, the electrons stay behind, okay? Or we break that bond and one electron stays, one electron goes. Those are three different possibilities. There's chemical transformations that can do either of those. The important thing is not what chemical transformation I'm actually doing, but what is being left behind. So in this example, what we're going to do is we're going to take the hydrogen and its electrons that it is sharing with the carbon. And so in doing so, we generate the carbocation upstairs, right here. All right. And so because this starting material is cyclopentadiene, this would be called the cyclopenta, I should say, dienyl cation. And so then the question is, How many pi electrons do we see? Well, there's 2 pi bonds, 2 pi electrons for each of those. And so this particular example has 4 pi electrons. The Huckel output is 2, 6, 8. So this is an example of a cation that is not aromatic. Right? So this was not aromatic. The system is still conjugated because we can draw the resonance functions. The double bond on the right here can flip up, moving the cation downstairs to the right. The double bond on the left can flip down, moving the cation, carbocation up here. So this charge is resonated all around the ring, which means the pi electron density is resonated all around the ring. So it's still a conjugated system. It just doesn't have enough pi electrons to be qualified as an aromatic system. Now, the other possibility is if you steal the hydrogen and whatever reactant steals that hydrogen, it takes away 1 electron. And because you know that covalent bond is sharing 2 electrons, if it takes away 1 electron, then this is going to be an intermediate that generates a radical. And so rather than a carbocation like the example upstairs, we have a free radical situated at that carbon upstairs. And so then this is called the cyclopentadienyl radical. And then that radical, because it's an electron on a carbon whose outer valence electrons are the p orbital, will count towards the total count of the pi electrons. So in this case, this has 2, 4, 5 pi electrons in the system. The Huckel output is 2, 6, 10. So this example, still not aromatic, but still we have resonance electronic communication all around the ring, because we can flip the double bond up, radical moves bottom right, that double bond on the left can flip down, radicals upper left, so we can still have resonance around the ring, but it's still not an aromatic cyclopentadiene tetrahedral. The third one is if all we're going to do is take the proton, which means the electrons that are being shared between the carbon that's holding it there get left behind. Whenever electrons get left behind, that means we're generating a carbanion, and that's a carbon that's got more electrons than it needs, so it has a formal charge of -1, and we usually show that there's 2 electrons situated there. And those 2 electrons for the carbanion, and we're going to see carbanions as really important reactants, right? So in OChem 1, the star of the intermediate star for those reactions was a carbocation intermediate. Later on in the semester, we're going to see that carbanion is a really important intermediate as well. It basically behaves as a really strong base. But in this case, we start to count those pi electrons, right? So this, which we will call the cyclopentadienyl anion, now has 2, 4, 6 pi electrons. And the Huckel output is 2, 6, 10, 14. So having 6 pi electrons does qualify as aromatic. And so this anion is an aromatic ion. So it does have that added stability. Whereas the cyclopentadiene radical and cyclopentadiene cation. So I guess, having gone through this exercise, I'm going to show you one more with a 7-membered ring. But the take-home message here is that when you start counting the pi electrons, if the radical, the cation, or the anion are at arylic positions to double bonds, then you still got conjugation around the ring. Then it's just a matter of counting the total pi electrons to see if they match the Huckel output to determine whether or not it's aromatic. Right? And of course that can change because necessarily when you move from a 5-membered ring like this to look at the three different possibilities for example, 7-membered ring. So here you get to practice drawing your 7-membered rings. Let's say you have the cation, the radical. Come down here and draw the anion. Bless you. Here are the three. So the first one is the cycloheptacation. And we have the cycloheptational radical. And then here we have the cycloheptational anion. Now, applying what we learned from the previous example of cyclopentadiene, which one of these is the aromatic variant? The first one, the second one, and the third one? Somebody say the first one. This one, the third one. Got 2 for the first one now. How many pi electrons does the middle one have? This one. 7. How many pi electrons does this one have? 8. How many pi electrons does that one have? 6. So 6 pi electrons. 2, 4, 6. This one has 2, 4, 6, 7 pi electrons. This one has 2, 4, 6, 8 pi electrons. And so we agree that the Huckel output is 6 because it goes 2, 6, 10. It's the first one that's aromatic. Right? So all 3 of these are conjugated, all 3 of these can resonate around the entire ring, but only the first one with 6 pi electrons is the aromatic variant. The other 2 will be very bad. Any questions about this? All right, so I kind of alluded to last class period that there's a whole host of other aromatic molecules. There's a whole host of fused bicyclics that I'm going to show you that are aromatic. But what really sort of opens the floodgates to a lot of these structures, and in fact, the synthesis for the molecule that I'm going to teach you how to make in 2 of the lab sections of this class is an example of a 5 ring system, and the whole thing is aromatic and conjugated. So that particular synthesis starts with 3 aromatic rings, and we do 2 cyclization to make 1 product to make 2 other rings, and everything ends up being conjugated. And so that example is going to be an example of what we call an aromatic heterocycle. All right? And aromatic heterocycles, unlike the molecules that we've been dealing with right now, are going to be comprised of rings that have other atoms in them that are not carbon. And so, of course, now you start thinking like, wow, okay, we look at an aromatic ring like benzene's got 6 carbons in it. You can replace one of those atoms with nitrogen or sulfur, for example, oxygen. Now you start getting heterocycles. Of course, those rings can be 6-membered, 5-membered, 7-membered. So the ones I'm going to teach you here are going to be probably some of the most important ones that you'll probably see at some point, depending on what your career goals are, but these are pretty important aromatic heterocycles. And this first one is known as pyridine. Now, for those of you who took it with me, it depends on what you covered. But in chapter 3, chapter 3 or 4, I think it's 3, of OChem 1, we talk about acid and base chemistry. And as we make the leap from Arrhenius to Bronsted-Lowry, the reason we did that is because Arrhenius acid-base theory doesn't take into consideration that amines behave as bases, right? Because Arrhenius acid-base theory said that a base generates hydroxide. So then sodium hydroxide, potassium hydroxide. And then acids generate H+, which is hydrochloric acid, sulfuric acid. But then it didn't explain why ammonia, for example, ammonia is a base, but ammonia doesn't generate hydroxide. So we shifted in definition to talk about proton donors and proton acceptors, right? And one of those bases, one of the very common weak bases, happens to be pyridine, right? And it's basic because what we learned from once we moved to Lewis acid-base theory is that if you have a heteroatom that has a lone pair of non-bonding electrons, be it oxygen, sulfur, nitrogen, these are what attack the acids. And so pyridine is a very common weak base. If you happen to be in its vicinity and work with it, if you have testicles, this thing will make you sterile. If you don't have testicles, you don't have to worry about it. That doesn't mean go bathing in it, right? I'm not saying that. I'm just saying this is what will happen to you if you get it on you. But it's a really important base. In fact, my examination for the first exam of OChem 1 has a reaction where this thing is reacting with either carboxylic acid or a mineral acid, where we draw the curved arrow formalism for generating what is known as pyridinium, which is once that nitrogen grabs that hydrogen, it now has 4 bonds to it, which makes it a formal charge of +1. So this one's really common, and it is a weak aromatic heterocyclic base. Here's another one. And this is pyrimidine. Now, if we were to analyze these aromatic structures, without you having read the textbook, without you coming to lecture so I can teach you what I'm about to say, is that if you were to count the total pi electrons, you would be mistaken if you included in that count the lone pair of electrons on these heteroatoms, at least for these 2 examples. And so the correct way to count the pi electrons for this is that it's 2, 4, 6. We ignore the one on the nitrogen here. For this one, it's 2, 4, 6. And we ignore the ones on these nitrogen. And we ignore those ones in the hydrogen, the nitrogens there, for a very good reason. Because remember, what we're trying to count are pi electrons. And in order to be a pi electron, those electrons need to be in the p orbital. All right? Now, if that heteroatom, as is in both of these cases, isn't already engaged in a pi bond, then it is already using those p electrons to make the pi bond. So the answer is, if the nitrogen has a double bond on it, then you don't count its electrons, lone pair. You don't. Right? So that one clearly has a double bond on it. This one has a double bond going to the bottom left. That one has a double bond coming downstairs from the nitrogen. So in those cases, it means that that lone pair is not coming from the pi orbital, or from the p orbital, I should say. So what I can do is we can draw pyridine line like this. And so this kind of sets the stage for us to also understand a little bit of its basicity. So here are the p orbitals that are engaged in the pi bonds. Here's a pi bond, here's a pi bond, and here's a pi bond. So as drawn, in order to form the pi bond that we see between the nitrogen and this carbon, those p orbitals are already occupied. What it means is the lone pair of non-bonding electrons actually sit perpendicular to the plane of the p orbitals engaged in that pi bond, like this. right? That's the space that they occupy. And this lone pair, in this instant, is in the sp2 orbital. And because of that, they don't count as pi electrons. The pi electrons for that heteroatom nitrogen are already engaged in the pi bond. So when we count all the pi bonds, 2, 4, 6, we've already taken them into consideration, whatever nitrogen has to give. All right? And this is precisely why these examples of pyridine and pyridine are bases. This is why they're weak bases, because the lone pair of electrons in this case are not in a p orbital engaged in a pi bond. They're out there perpendicular to the plane of the ring, and perpendicular to the plane of the pi bond, p orbitals. These are the ones that attack the acids. When we draw that mechanism of attack, that's where they're coming from. Now, I want to show you a few other aromatic heterocycles so that you can see what I've told you put into practice outside of these examples. This right here is known as pyrrole. Do you see any pi bonds to that nitrogen? No. That means the lone pair of non-bonding electrons on that nitrogen do get counted. They do get counted in the total pi electron count. So in this case, it would be 2, 4, 6. Pyrrole is an aromatic heterocycle. Let me show you the imidazole. Imidazole is an interesting one. There's a pi bond to the nitrogen upstairs to the right, but there are no pi bonds to the nitrogen downstairs. So when we count the total pi electrons, we see 2 pi bonds, so it's 2, 4, and then 6 if we count this one, but we don't count the lone pair on that nitrogen that has the pi bond to it, right? So this is a really good example of one nitrogen which has a lone pair that we do count, and another nitrogen which has a lone pair that we do not. This molecule is named imidazole. And so just to sort of wrap things up, let me show you the orbital diagram, not the orbital diagram, the orbital overlaps. Pyrrole. And I write that the lone pair, like we discussed, is situated in the p orbital, so you do count that. So 2, 4, 6. All right. So as long as you remember that, right, with these types of molecules, and you'll be able to determine once you've memorized the Huckel output, which one of these are aromatic and which ones are not, or how do we count them correctly. I mean, the easy way would just be to remember these things, but what if I throw a molecule at you, for which there are many that you've never seen before, that has this kind of thing happening in structure? And then outside of memorizing these ones in the notes, you'll have to apply what I'm teaching to something you've never seen before. Does anybody have any questions about this? Yeah?
On the exam, will you show the lone pair in like a question like this?
Sometimes I do, sometimes I don't. Yeah. So lone pairs are not always shown. So it's always a good, as I kind of mentioned in the vocab model, it's always good to remember which ones happen. Any other questions about this? Anybody still need this up? All right, so I'm not going to torture you too much. Now I'm going to show you a few polycyclic aromatic hydrocarbons that I will require you to memorize. There will be a problem or two because these are pretty common. But I'm not going to torture you by generating polycyclic aromatics, which also have too many heteroatoms. Let's see what I have here. I've got maybe 3 examples. But if you were to come into my research office or my research lab, I've got a poster that's just full of them to give you an idea of how many there are. There's just a lot. But we'll start simple. This structure right here is naphthalene. Now, you may or may not have smelled naphthalene before. Maybe you know some old aunt or uncle, perhaps your grandparents, maybe your great-grandparents. It used to be common practice down here in the South to put a box of mothballs in a closet or in your drawer. And it wards off moths and roaches, because moths and roaches, whether you know it or not, if you have clothing that's made of real stuff, you know, not the polymers we make now, they will eat holes into your clothes. It used to be a big problem. So have you ever smelled mothballs? That smells a really distinct smell. That's the smell of naphthalene. So you know what mothballs smell like, they're naphthalene. If you're interested, I think they sell them at HEB. If you just get the box, you don't even have to open it. Just you'll smell it right away. Like, oh, that's naphthalene. If you don't know what mothballs are, then maybe you're just really young. I'm showing my age. This is anthracene. This one is pyrene. One of the things that's really interesting about naphthalene and anthracene and pyrene is these structures are actually luminescent. So if you hit them with UV light, they will fluoresce very brightly. So if you remember in our discussions for exam 1, we talked about luminescence. And the idea was that when you shine electromagnetic radiation, maybe in the UV range, to a molecule, it will excite the electrons to an excited state. And some of that energy gets excited because the molecule can rotate its bonds and it can start to bend. And basically you lose the energy via radiation decay. Motions that we see when we talk about infrared spectroscopy, the molecules start to dance and the energy starts to drop. Now, as you start to rigidify molecules, you hinder that rotation. These molecules are absolutely rigid. They're planar and flat like a plate. But when you excite them, they can't rotate, right? Bond rotation around these kind of structures is forbidden. And so, as a result, as you go from left to right, pyrene is a very, very, very bright fluorescent probe that's used in not only the chemical sciences, but also the biological science. So it's not unusual to see anthracene or pyrene having a side chain that you can use to functionalize, for example, amino acids or different proteins. That way, when you irradiate them under what is called a fluorescence microscope, you can see where they are in the cell. You know, and sometimes you can design these things so that they go straight to the nuclear membrane, straight to the cellular membrane, or maybe they remain in the cytoplasm, maybe they have organelle-specific binding sites, and so you can illuminate selectively the mitochondria, things like that. But the idea is that you get them excited and then they start to glow for you, and you can see them. So these ones are pretty common. Here is a sort of naphthalene-like structure that includes a pyridine in it, and this is known as quinoline. Right, this is an example of a bicyclic, polycyclic, polyheterocyclic aromatic. This one is pretty important. This is indole. So you've got a 5-membered ring, we have a nitrogen right here, we have a double bond right here, right? Indole is the group that you see on the amino acid tryptophan, which we use to biosynthesize neurotransmitters such as serotonin and melatonin. This is period. Just saying, this is a single bond right here. I screwed this up royally. Here's the double one. Both the nitrogens have a double bond together. And then the last one I want to show you. This one has all kinds of fun derivatives, but I'm not gonna charge you too bad. This right here is phenanthine. Phenanthine is kind of neat because there's a variant in which these two carbons are actually nitrogens. And those molecules can coordinate to metals. And so they're used to generate sort of organometallic type complexes that are used for catalysis. But this would be, similar in structure for those molecules, let's say. All right, so for the last part of this chapter, what we're going to go over is a series of chemical reactions. And these chemical reactions are going to be focused on groups that are coming off of an aromatic ring. All right. So now that we've established that the aromatic ring, because it is aromatic and has that high activation barrier for some of those chemical transformations, it means that there's a lot of chemical reactions we can do to groups that are already on them, and we don't have to worry about touching the aromatic ring. Yeah.
Could you show pyrene? I wonder if there was a
I'm thinking I might be missing a pi. Let me see. So, double bond, single bond, double bond, double bond, single bond, double bond. There, I think there is. I'm thinking there should be there should be one here, which means that shouldn't be there. I'll have to go back and look. I think I am missing a pi bond. I might have gotten ahead of myself. One of those rings has one pi bond in it for sure. I think I've switched them. Does anybody still read this up? All right, so I also want to preface what we're about to go over is that we will see a lot of these reactions again, because as we go through these chapters that are coming up, there is a chapter on alcohols. There is a chapter on carboxylic acid and carboxylic acid derivatives. There is a chapter on aldehydes and ketones and things like that. So there is going to be a fair amount of overlap in the reactions as we go from chapter to chapter, which is a good thing for you. It means you don't have to memorize too many crazy reactions, but if you thought there were a lot of reactions in OChem 1, I can tell you that there's double to maybe 3 times as many reactions in OChem 2. So again, use your time wisely. So the first set of reactions I want to talk about are oxidation of aromatic compounds. Now, when it comes to the real definition of oxidation and reduction, we know with regards to metals, we're talking about reduction being adding electrons into the system and oxidation meaning electrons taken out. But with regards to what we're looking at now in OChem as for chemical transformation, the same is still true, but usually it means we're increasing the oxidation state, which either means we're putting oxygen into the structure or we're increasing the number of bonds to oxygen. Okay? And so, luckily, as I pointed out, benzene rings are inert to strong oxidizers. So if we had a substrate like this, so here we have an aromatic ring, and coming off of it, we have a butyl chain. The first oxidant will be potassium permanganate, which is KMnO4. In order for this to be a strongly oxidizing, it's already a strong oxidizer, but in the presence of water, it's even stronger. This reaction usually requires two steps. It usually, when you run this reaction, you generate a carboxylate anion. So normally when I throw a reaction at you like this, I will say 1 potassium permanganate water, 2 hydronium, which is H3O+, which is an acid aqueous workup. So here I'm going to show it as 2 different steps. But under these conditions, which we can consider strongly oxidizing, is we take the carbon at the benzylic position to its highest oxidation state without breaking a carbon bond between it and the aromatic ring. So when we look at the original substrate, the bond that is breaking is this one. This bond right here is gone, right? This bond right here. This position right here, you probably might not remember, but this is what we call the benzylic position. Okay? And if that benzylic position has hydrogens on it, then this transformation will happen. Okay? So the highest oxidation state you can take carbon, right? Highest is carbon dioxide. And in order to do that, you break every carbon-carbon bond. So when you burn things, right, you get 2 products. You take hydrogen to its highest oxidation state, which is water, and you take the individual carbons to their highest oxidation state, which is carbon dioxide. These chemical reactions take that carbon at the benzylic position to its highest oxidation state without breaking that last carbon-carbon bond between it and the aromatic ring. So right before the thing gets burned to generate carbon dioxide, the closest thing you can get is the carboxylic acid. When you look at a carboxylic acid, that's technically the highest oxidation state you can get right before that thing pops off as CO2. I mean, you can already see it. You've got a carbon, you've got 2 oxygens already there. Once you break that carbon-carbon bond, it's carbon dioxide. You burn it, right? But this one isn't burning it. It's stopping just shy of breaking this bond right here. And you end up with the carboxylic acid. Another reagent that can pull this off is sodium chromate and sulfuric acid. This generates the in situ chromium 6, which is, kind of nasty stuff. I don't like these kinds of reactions. If you've ever seen, what's that movie with Julia Roberts, where there's chromium contamination in some, you guys remember this movie? She's working with a lawyer's office. I can't remember the name either. Man, I just saw it, like a few weeks ago. I think it was on Netflix or something. Aaron Brockovich, yeah. Aaron Brockovich. So there's a chemical company who was having these collection ponds that I guess they didn't have a liner. What they were doing where they was using chromium-6 as a catalyst tube for whatever petroleum or whatever kind of industry they were doing, and then that was getting into the groundwater and people were getting all these cancers and horrible. This is that kind of chemistry, whatever they were doing. They in situ generate chromium-6 to pull off this oxidation. And again, it's the benzylic position. So it's the carbon directly attached to an aromatic ring that's oxidized. Anything else is cleaved, right? So that chain could have been 10 carbons long, you still end up getting benzoic acid. So it cleaves that bond there, that benzoic position gets the highest oxidation state without getting the aromatic ring cleaved off. Let me show you another type of oxidation. So here we have paraxylene and the presence of oxygen and cobalt-3. It's the same transformation. We get aromatic carboxylic acids generated. And again, it all hinges on whether or not the benzylic positions, which is the carbon directly attached to the aromatic ring, whether or not those benzylic positions have hydrogens. They have to have hydrogens for this to work. If there's no hydrogens, it's not going to work. And so, at some point, at least in the chapter of alcohols, we're going to talk about the different types of oxidations that can be done. If you start with a carbon-carbon double bond and you oxidize it once, you get the alcohol, right? If you oxidize it one step further, depending on where the alcohol is, you either get the ketone or the aldehyde. If it's on the last carbon, you can oxidize it one step further to the carboxylic acid. So in all these examples I'm showing you here, we're going all the way to the carboxylic acid. Again, highest oxidation state before we burn it, okay? But maybe you don't want to go to the carboxylic acid. Maybe you want to stop one step before the carboxylic acid, which would be the aldehyde. And that can be done. So if you had something like benzyl alcohol, notice that we still have benzylic hydrogens there. That's a CH2, there's two hydrogens there, so it'll work. The new reagent that we're going to use here is known as PCC, and that is pyridinium chlorochromate. We'll analyze that a little bit further in the semester, but for now, just know it's PCC. And that oxidant is not as strong, and it will stop at the aldehyde, right? And so the aldehyde is technically the step right before you get to the carboxylic acid. The carboxylic acid is a step right before you burn it. Right? So PCC will take you to the aldehyde, whereas cobalt-3, sodium chromate, H2S4, and potassium permanganate and water will all take you to the carboxylic acid. Now, I want to annotate the notes just so that way, for those who haven't written it down yet, this mechanism involves benzylic hydrogens. Which means if there are no benzylic hydrogens, then you get no reaction. So let me give you an example. If you have terbutylbenzene, there is a benzylic carbon, but it has no hydrogens. This is an example where we have no benzylic hydrogens. So something like this, if you chuck potassium permanganate and water at it, or if you hit it with the in situ synthesis of chromium-6, which is sodium chromate and sulfuric acid, both of these result in no reaction. So if you had an aromatic ring, for example, on one end you had the tert-butyl group, and at the para position you had a methyl group. Subjected to these oxidation conditions, you will only affect the methyl group, and your tert-butyl group will remain intact. Give you that catch right there. Now, back in OChem 1, in the chapter of alkanes, you know, we talk about how alkanes are the most predominant organic molecule on the planet. The reason for that is because there's really three chemical reactions that we undergo. One of them is we burn them, which is what we do when we burn gasoline, you know, things like that, lighters, propane. So oxidation is something that happens. The other one is hydrocracking, which is the process that we do over in the refineries, where if you take something, for example, like a C12 hydrocarbon, and you burn that, that oxidation process is kinetically slower than something with smaller carbons. So if you're in this business of generating jet fuel or gasoline, these long hydrocarbons coming out of the ground need to be broken into smaller pieces. And that is known as hydrocracking. So we basically break them into pieces so that they're more useful for gasoline or additives or possibly jet fuel. The third reaction that they can undergo is radical halogenation. And the example that I give in OChem 1 is that if you take, for example, chlorine gas and methane, in the presence of UV light, you can generate chloromethane. That reaction is a reaction that propagates and propagates until it terminates. So not only do you generate chloromethane, you generate dichloromethane, you generate trichloromethane and carbon tetrachloride, right? And once you get to carbon tetrachloride, that reaction stops. And so because hydrocarbons are susceptible to what we call radical halogenation, that is going to be a new set of reactions that I'm going to show you. All right? Anybody still need this up? Now, this reaction that I'm going to show you is actually a reaction, one of the first reactions I ran when I got to graduate school. And it's a pain in the ass, and I'll tell you why. It's a pain in the butt, because what you really don't learn is that nobody's kitchen is the same. There's some chemical reactions. There's always going to be something a little bit different, despite our best efforts to mimic the exact conditions of a laboratory, for example, up north at Northwestern, or my laboratory in Tianjin, China, which is a very different humidity, temperature characteristics. I mean, there's all kinds of variables that we just don't take into consideration. It's hard to take a published synthesis and duplicate it exactly in multiple locations. You have to tweak a little bit of things here and there. All right? Now, this reaction involves a reagent known as NBS. We usually run this reaction in a mixture of dichloromethane, which is CH2Cl2, that's the organic solvent, and carbon tetrachloride. And then we usually heat this, oftentimes to reflux. So that little triangle means that we're going to heat it or possibly reflux this reaction. One of the things that's really important for this reaction is it usually needs to be irradiated with UV light via a UV lamp, or, as I pointed out before, one of those flood lamps that uses the light bulb with the glass protection removed. You can buy them from Home Depot. They look really good. And what you end up getting is bromination at the benzoic position. This reaction is specific for halogenation at the benzoic position. Now, NBS is a special reagent, and it stands for N-bromosuccinimide. I'm going to come down this way. They also have NCS, which is the same thing except it's chloro. So you can use it to do radical chlorination. And the great thing about NBS, if you go back to the original reaction that I made reference to, the source of chlorine would have been chlorine gas. Now, chlorine gas and working with chlorine gas is a big pain in the butt. It means you need to generate it somehow. You need to be able to funnel it into your reaction, which oftentimes means you got to bubble it into there. And even then, a lot of it escapes. And then you got to make sure that that doesn't get into a room of people. It's got to be ventilated, right? There's that. If you want to do the bromination, it means you got to work with liquid bromine, which is also a pain in the butt, right? It's just not great stuff to work with. And not only that, like let's say you want to control the stoichiometry of chlorine. Maybe you only want to brominate it once or chlorinate it once. Then how do you do that with a gas? It's not easy. N-bromosuccinimide and N-chlorosuccinimide is a solid, which means we can weigh it out, all right? And so because of that, NBS is the preferred choice for generating bromine and chlorine chlorinations via radical conditions, because we can control the stoichiometry very precisely, because for every one molecule of NBS, you have one molecule of bromine. And so what that structure looks like is it's this. Right, so every 1 molar equivalent of NBS or NCS, you have 1 molar equivalent of the halogen that you might be using. Right? However, there's still a problem. There's still a problem. Let me show you the reaction that I was tasked as a very young PhD student. There is a publication, the molecule that I needed for the second step in the synthesis was really, really expensive, so I had to make it myself. And these were the conditions. It was NBS, dichloromethane, carbon tetrachloride, UV light, and AIBN. AIBN is a radical initiator, and what I wanted to do was to brominate both benzoic positions just once, to get a derivative like this, dibromoparaxylene. Now, the one I was actually trying to make had an iodine position next to one of those methyl groups, so it's not exactly the same, but it's the same transformation, so I'm keeping it simple by removing the iodine in the final material. Now, one of the things that I learned right away was that this is not one of those reactions that you can set and then just let it run for 24 hours and then stop it, right? And the reason for that is if you let this reaction run for longer time, then this is what happens. You get over-halogenation. And it turns out that however many hydrogens are on that benzoic position is how many halogens you can put at that position, of course, within sterics, right? At some point, 2 bromines, you probably couldn't put 3 there. It's not going to fit. That's a problem. And so I kept on getting over-bromination in my reaction. And it became clear what I needed to do. I needed to follow this reaction via TLC from the very minute I set it up. And so when you run the TLC, it means you got your spot for your starting material, and at some point that spot starts to disappear and a new spot appears. The first spot that starts to appear is when one of those methyl groups gets brominated. The second spot that appears is when the other one gets brominated, or that one up there gets brominated twice, and they end up running, very close. Turns out I followed and babysat this reaction. for 18 hours. That was the magic number. I did nothing but TLC for 18 hours. Now granted, it was every hour, but it meant I couldn't do anything, especially I was in Los Angeles, right? If I left home, that was at least a 2-hour trip to it wasn't gonna happen. But the trick was, I only needed to do this once. Once I figured out that it was 18 hours and that was a sweet spot, I would just set it up, I would time it right, and then 18 hours later, I would just come back, work it up, and it was perfect every single time, right? But this is a really important point, is that radical brominations, radical reactions, they propagate until they terminate. And in this case, they will propagate until every single benzoic hydrogen has been substituted. So we gotta be careful about that. So the first set of reactions we looked at were oxidation of aromatic compounds. Now we're going to talk about doing the opposite. We have seen reduction reactions in OChem 1. Any reaction that involved hydrogen gas and palladium on charcoal, or platinum oxide, or nickel, for example, to take the double bond and make it a single bond, or to take the triple bond and make it a single bond. Or we use Mindler's catalyst, for example, to take a triple bond and convert it to a double bond. Those are all reduction reactions, right? And so, of course, for this first example, we're talking about alkenes reduction, or the reduction of alkenes. And so, if you remember, the aromatic double bonds in the aromatic ring, they don't react like alkenes, which means if there's alkenes present on the side chain, we can target those exclusively, right? And so if you take something like any of those reactions that we learned in OChem 2, which involved the palladium on charcoal, the platinum oxide, or the nickel, in the presence of hydrogen, everything on that side chain that's got a pi bond will basically reduce. So we can remove the carbonyl, we can remove the alkene very easily. Now, it is possible for the aromatic ring to be reduced. It's not impossible. It just has a higher activation barrier, which means we must use platinum and high pressure. So I was checking the precious metals this morning because I like to keep track of gold and silver. The precious metals include platinum and palladium. So since they're in the commodities index, right now platinum is $2,100 an ounce, palladium is $1,655 an ounce, right? So now that you see, oh, okay, the activation barrier to reduce the aromatic ring is higher, you need to use a platinum catalyst. You're also saying we got to use much more expensive chemistry. So platinum is much more expensive than palladium by almost double, or something like rhodium, which is even more expensive, is not considered a precious metal, rhodium and carbon. And so to give you an idea of what this can do, you can take something like orthoxylene. Those conditions might be hydrogen gas, platinum, at 130 atmospheres, right? If you're not familiar with that, atmospheric pressure, 1 atmosphere is what we experience now. So we're talking about 130 times atmospheric pressure. So this is in a pressure vessel. That can be done a variety of ways. Oftentimes it's glassware that is very thick walled. It has a valve on top that will burst or release pressure if it exceeds a certain limit. And normally when we run a reaction like this, we do it behind a blast shield, because at 130 atmospheres, it's effectively a bomb if the flask fails. But you can definitely take that thing and remove all the double bonds in the aromatic ring. Now, why you want to do that, I don't know. It's expensive, and cyclohexane is just when it comes to like commodity prices, it's just cheaper. You're taking a step back in complexity, molecular complexity, it's just a cheaper stuff. You look at a bottle of benzene and a bottle of cyclohexane, the prices are very clear. Right? But if it's part of a total synthesis for the next cancer drug, then maybe you might want to do that. Here's benzene. Here's another condition. This is using nickel, which is significantly cheaper. Nickel is not as good as a catalyst. So even if we pressurize it with nickel, we have to heat this up to 150 Celsius to get it to work. So we use a cheaper catalyst, but now we have to put temperature into the system. And even at 100 atmospheres, we still need a blast shield, make sure that thing doesn't pop, and then we're good. But if we want to go back to the good old chemistry that we saw in OChem 1, we can take something like styrene, which has a pi bond that's outside of the aromatic ring, and then just the good old reaction from OChem 1, platinum, at 2 atmospheres, room temperature. And we can convert styrene to ethyl benzene. Pretty straightforward. So lucky you guys, I've got like maybe a page and a half left of notes and 3 minutes left. Which means you guys get to go to spring break and we get to have a class on Tuesday where we finish this up before we start the material for the 3rd exam, which would make the exam not the week you come back, but the week after. All right. So we'll finish it up on Tuesday, May 4th.